Okay, we're doing power. Last lesson of Physics 11. Here. It is kind of sad. I'll miss you guys. You're a good class. I've asked you the difference between power and energy. You can sum it up in one word. Does anybody know the word? Oh, who said it? Someone said it.
Time.
Jeffrey. Time. Okay, let's give it to him. Go. That's it, though. That's the last one. Yeah, power is energy over time. So we might say that power is the rate of doing work. Put, what is work? Thanks, Put. Put, what do you think work is?
To make an action or anything.
Okay, make an action, move, or anything. Good. And some other people said it's FD. Is it net force times distance? Applied force, or whatever force is doing the work, right? What is a rate? What does that mean? What's this? Iman, what does this mean?
Rate?
Yeah. Do you know? Who can say what a rate is? Ty, you got an idea?
So like kilometers per hour.
Okay, yeah.
Hour is like joules per second.
Right. That's a very good way to say it. Gordon.
Amount of rate of change.
Ah, rate of change, yeah. So rate involves time, right? Whatever is changing, as Ty says, per time. And Gordon is absolutely right. There's a change involved, right? So this change and work over time. So oftentimes people say power and work are kind of the same thing. Like electricity is like, oh, it's power, it's got power, which is true. But power and energy, power and work, not the same thing. So the difference between them is time. Energy is energy. It doesn't rely on time. It doesn't matter how much time. Oh, by the way, if you know Jaffe Kirkshank, he's doing a good design lab with marshmallows. He's blowing them up in the vacuum chamber. And he left the marshmallows out last night. And if you look from here down over to there, right by Mila's feet, and then back to the end of the classroom and out the door, there's a little highway of ants in the classroom now. So be careful, because we don't want to crush them while they're doing work. They showed up overnight. Yeah. Power is measured in watts. The unit of work is watts. And 1 watt is equal to 1 joule per second. Good. One watt is equal to 1 joule per second. And so power is equal to work over time, or a change in energy over time is another way to think of it. Don't get confused with the 2 W's. One is work, which is measured in joules. This W is watts, which is the unit for power. Power is in watts, which is a joule per second. Work is in joules, time in seconds, so joules per second equals watts. Okay, who here likes cars? Danny, what's your favorite car? R34? What is that? Nissan? Is that a car?
Yeah.
Why do I not know that?
R34 is the number, like R35.
Okay, so Danny said his R34. It's a powerful car, yeah? Okay, and I'm gonna race him in my dented old pickup truck. Okay, it's out there. You can see it. It's very rusty and dented, and it's not that powerful. And we're gonna start on Mathers at this side of the school, and we're gonna race. So Dylan stands out there with flag. I go, "Wah!" and Danny takes off. He's way faster than me, way more powerful. And he goes to the other end of the school and stops, but I didn't know the race ended there, so I just keep on driving. And I drive all the way out to Horseshoe Bay. Who burned more energy? Me, I did. Because I went way, way, way farther, right? But who was more powerful? Danny. Because in that same amount of time, he did more work than I did. He went farther than I did, right? So power is all about time. Energy just adds up. Okay, try this. Oh, you can talk to me about that later. I'm teaching. What type of energy is she gaining? Potential energy, yeah. With potential energy, which distance do we want to use to calculate that? Are we using the 4 or are we using the 2.5? If we knew the force she was exerting, we would do the force times this distance, right? Do we know that force?
No.
But we do know what force.
Force of gravity.
Saul, say that again?
Force of gravity.
Very good. Yeah, we know the force of gravity. So if she was being lifted straight up, it would be what formula?
MGH.
MGH. So we're going to use the 2.5 in this case. If we knew her applied force, we might be able to do this times 4. Is the change in her potential energy the same as the work she has to do to go up the ramp?
Yeah.
It is in this case. Why?
Because it's like constant velocity.
Oh, I didn't say it here. You should be asking me a question.
Is there heat given?
Ah, good. So is there friction? So we'll say no friction. Thank you, Mila.
There's no friction, then not go up.
If there was friction, then her work would have to be a little more than the than the potential energy she gets out, right? But if there's no friction, her potential energy gain would be the same as the work she had to put in.
If there was friction, be equal to potential energy plus heat given?
Yes,
Okay.
that's correct. Yeah, and let's say that again. If there was friction, Mila's saying her work done, her force times the 4, would be equal to this potential energy plus the heat that she's giving off while she...
So if there was friction, how would you solve this problem?
Well, then I would have to give you the force applied. You do the force applied times 4. That would be the total work.
Okay.
And then you'd have to subtract this to get the heat given off. It is so hot. I'm just going to open this window.
Would you use the work minus friction?
If you knew the heat, you could do the work minus the heat, and that would give you this.
And that's what you want to use to find the power.
Yeah, so let's do this with no friction. So let's find the potential energy she gains. It's 60 times what?
9.8
times 2.5.
Yeah, can we do the 9.8 times 10?
Yeah.
Okay. And my height is 2.5. So that's 600 times 2.5. 1,203 is 1,500. Is that right?
Yeah.
Check.
The real answer is 14.7.
Yeah.
Okay, 14.7. And then that's it. So is this energy or power?
Energy.
This is energy, right? Okay, so how do I find the power then?
Divided by the time.
Good. So my power is my work over time, or my change in energy over time. This is the change in energy. how come this is the change in energy? Isn't this just the potential energy of her at the time?
The kinetic energy, kinetic energy is potential energy.
Okay, yeah, Ty?
Because kinetic energy and potential energy are always going to equal the same.
Okay, yeah, sure. What was her potential energy at the beginning?
0.
0.
Good. So down here, her EP is 0, right? So her change in energy is going to be mgh, yes? So this is my kind of delta energy, which is also equal to my work, right? Okay, so my work divided by the time, what's 1500 divided by 4.5?
333.3.
Thank you, Robin. 333, and what would my unit be? Good, you could put watts. Again, this W is for the unit of power, watts, not for work. Okay. Could I also say joules per second here? Yeah, that's fine. If you want to write J/S, bless you. That's fine too. Try this one. Read this. Don't worry about the numbers right now. Turn to the person beside you and decide how you would solve this problem. What are the steps?
So I would find.
Well, that is how you divide it by 4.
Is there only one way to do this question? There's more than one way to do this, right? Who found the acceleration first? That's understandable because you remember your kinematics training, right? And you have a car that accelerates from rest up to a VF, and you know the time, so it should be pretty easy to find the acceleration. So let's talk about that way first. If you find your acceleration, what can you then, can they see me over here?
No, not right now.
Right here?
No.
No, you're right now.
If you find the acceleration, what then can you find?
The distance.
You can find distance, and you can also find force. Good.
Distance helps.
Because we need distance to get the work.
So if you multiply the acceleration by the mass, what does that tell us?
F
F net, right? Now, is there friction here?
No.
No, it says ignore friction. There's no friction. So if there's no friction, then my F net is equal to what? Good. Good, Elena. Applied force is going to be the same as the net force because there's no friction pulling back. Okay. All right, if you know the FA, then what can you find?
Work.
Good, that's all good. Work is a fad, right? If your applied force is the one doing the work, you can do applied force times the distance, which you could have gotten with using the acceleration. Okay, and if you know the work and we know the time, what can we find then?
Power.
Then we have power. So, I encourage you to do this. If you get a question like this and you're like, I don't see it all at once, do this part first. So, you're going to find acceleration first, and then you're going to use that to find the applied force. and then you're going to use that to find the work. Well, I guess you got to get the distance from the side.
I have a question.
That's 3, and then you use the work to find power. That's 4, and then you're done. Yeah.
Watts and work have like the same symbol, isn't it?
Yeah, it's very confusing.
There you go.
So if it's in a formula, it's W for work. It's a variable. But if it comes after a number, then it's a unit, watts, which is power.
What's the first what's the first?
So if it's W, if it's a letter in a formula like this, that's work. This is work.
Wait, so how do you find watts?
Watts is the unit of power. So 1 watt, 1 joule per second.
But power is work over time.
Yes.
Oh.
So work
That's,
is,
yeah, that's so confusing.
it's confusing because this W is work, which is in joules. The unit of joules.
W times W.
Yeah, it's not, you'll get it figured out, but it is a bit confusing because there's 2 W's. Now there's another way to do this. Yeah, it's kind of simpler. Jeffrey knows. Can anybody else think about it too? Matt's got an idea. Dylan's got an idea. Ty's got an idea.
Isn't it we just have to find
Think about energy. Asol's just raring to go. Tell us, Asol.
Can I think energy?
What kind of energy?
EK.
Okay, okay.
Equal to 1/2 of.
Can we find the kinetic energy?
Yeah.
Yeah.
We know the mass, right?
Yeah.
And we know the VF.
Yeah. We just found the VI by the first
We
one.
don't need to find it says from the rest.
Oh right, yeah. So
You're right, we do have to know the VI, but the VI is 0. So what's the EK at the beginning? It's gonna be 0, it's not moving, right? So your EKI, I would say, your initial kinetic energy is 0. And so if you take the final kinetic energy, then that's equal to the change in energy. Right? So this is equal to kind of delta E, because you started with 0 energy and you go up to this final kinetic energy. That's our change in energy. Okay, good. So if we have our change in energy, what do we do then?
We just put in formula.
You just put it in here. Power, we said, was delta E over T, right? So this way is a little quicker with energy. It's funny, energy often simplifies a problem. But you could do it both ways, definitely. I think it comes out to,
938.
28.
that doesn't sound right to me. The VF is 15, so 15 squared is 225 times 500. Ooh, that's a big number. And then divide by 4. Maybe he's right. Is
I've
he
read
right?
28, 125.
28,125?
Yeah.
Yeah, that sounds close. 225 times 500 would be 25, 10,000?
2,200.
Yeah, about 25,000, 28,000 you said?
Yeah.
Yeah.
28, 125? And what would be my unit here, Elena? Good. So this is watts. Yeah, or joules per second would be fine. I'll post the video.
Thank you.
Are you going to karate?
No.
Ah.
To go do a fashion show.
Oh, okay. Enjoy the fashion show.
Yeah, you should come watch.
When is it?
It's at the Kimi.
Yeah.
Oh, okay. I will try. I'll try. Yes.
the formula we're using right now is the W equal. Or
P equals W over T. It's hard to see.
right.
I know it's faded out. I have to get someone to climb up there.
After
I'll do it.
W.
Yeah.
For the
Can you
I
ground.
got a
Sharpie?
ladder right here. Okay. That makes sense, that one?
Yeah.
I'm sorry. Okay, there's only one other thing with power. It's a kind of a special situation. What if you're not starting at rest? What if you're just starting at speed and carrying on going the same speed? If there was no friction, would that take any power? Would take no power. The spacecraft Voyager is just going along, but there's no force. So it's not doing any work, it's not accelerating, there's no friction, there's kind of nothing, right? Okay, but what if you're driving to school in your car? And you're just driving at a constant velocity. Are you doing work? Yes. Are you using energy? Yes. Okay, so let's look at this. I did this too small, apparently. If power is work over time, can you see this? I'll do it. I'll try to do it bigger. If power is work over time, work is force times distance, right? Maybe we might say force applied times distance over time, right? See anything interesting in there?
Not distance.
That's A.
Okay.
What's this? So, I love that when I see that. So, because d over t is velocity, then we can say P equals FV, just the force that's doing the work times its velocity, and that will give us the power. It's kind of a little trick, but it only works with constant velocity. If your velocity is changing, you can't use this. So, can the video see me?
Yeah, you can see, but I don't
Not
think
the
you can see
screen.
the
No,
full
they can't
picture.
see the screen, no.
Yeah.
I think you need somebody to hold it.
I know, I need a little remote. A robot.
That's fine.
Yeah.
Are we going to see any questions that say like you start at 15 meters per second and you go up to 25 meters per second?
Maybe. How would you do it?
Well, I would find the kinetic energy first, in
Yeah.
the first instance, and then
Yeah.
find the second kinetic energy, and the difference, and then use it for work over power.
That is correct. And that would be the change in energy, right? And so the amount of work would be the same as the change in energy. Put that over time, you get your power. Yes, absolutely. That's all.
What about that formula? P is equal to MV.
I'm glad you asked that question. Asal's asking a really good question. She's, what about that one? P equals mv. Isn't this power? So, it's another confusing thing. Elena, this is for you. P equals mv is not power. This is momentum. We used to learn it in grade 11, but we don't anymore. Don't worry about it. It's not for you. You'll learn it next year. I can teach you about it. I taught Gordon a little bit actually the other day. Wasn't that you? We were talking about momentum a bit. But this is not power. It's very useful, but you don't need to know this. So don't. That's not the power formula. The W over T is power.
It was just like the one like when I was doing like option.
Yeah, maybe that's what it was. Someone was doing collisions and stuff. Okay, try this. What's the answer? Quick. 308? Good. So if you just multiply this force, this is like the applied force. Multiply it by the speed, that gives you the power. Would this work if we were speeding up or slowing down?
No.
No. So you can only do this when it's constant velocity, but it's a nice little trick. I'm gonna give you a little worksheet right now. I'm gonna give you a little break because this is a two-part lesson. I'm gonna give you efficiency tutorial little thing in a little bit. But I will give you a worksheet first, practice. And I just want you to do 1 to 3. Yeah.
The question one before this one, it also says constant velocity, but you didn't use this formula because it says from rest.
I'm glad you asked that question, Dorson. Let's go back and look at it. This one?
Yeah.
Is it constant velocity? Not that one? Okay. Yeah. She is going constant velocity. And so you could do that if you knew her force and you knew her velocity up the ramp, you'd be able to calculate
Well,
her
we
power.
can calculate the force.
But we don't know those things in this situation. So
Can we
we'd have to
calculate
do
the
it this
velocity?
way. Hmm?
I mean, it's just we did second. We got.
You could actually, right?
We have the velocity.
We have a distance over time,
But we don't have the force.
but we don't have a force. But I could. We should do this. I could give you this situation and say, with what force is she applying up the ramp? Try it. Do it. Velocity is a little less than 1, right? And her power was. Do you remember what the power was that we got? Was it that much?
No, it was
333, that one, right?
Yeah.
So it would be power divided by this, so it'd be like about 350, 360 newtons, something like that. Should I write that out? I was talking then So if I asked you here, find the power, and then I said, find her force applied, we did the power from before, which Rodman remembered was 333 joules per second. And we also know she is going at a constant velocity, as Dorsa aptly pointed out. So we can say that this is force, and in this case it's force applied times the velocity. So her power over her velocity would be equal to her force applied. How do I know the velocity is just under 1?
Or 4.5 is just.
Yeah, her distance traveled, if she's running up here, she has norms. She goes 4 meters in 4.5 seconds, so my velocity is 4 meters over 4.5 seconds, and that's going to be 7, 8, 0.9? 88? Meters per second, and so that would be 333 watts over 0.88 meters per second, and that would be somewhere around 360? 37? And that would be in newtons. That would be kind of tricky of me. Now I have a good question for your exam.
Let's go.
Blame it on Dorsa. Yeah, Dylan, what were you saying? You definitely would have to find the power. So you'd still have to find the power the way we did it before. But then you'd have to use that answer to calculate this force. Okay. You have 10 minutes right now